sounds all around us. We hear natural sounds, such as the birds and the crickets and traffic and a fire truck, and we hear voices. We also hear synthetic sounds, sounds that are produced by musical instruments that are synthesized. We hear sounds that are just pure noise. They don't make any kind of sense to us. It's just a congobulation of different kinds of sounds all around us that don't make sense. And this is noise. But what is sound? Sound is any vibrating matter, and it's produced by some object which is allowed to transfer its energy in a simple way back and forth in an oscillatory or vibratory way. And when it does this, what it does is it presses against the air. And in places where the vibration is moving to the right, the air molecules in front of it get compressed, and the air molecules get behind it, get a little vacuumized or rarefied. And when it goes back to the center and then goes the opposite direction, the air behind it gets compressed and the air in front of it gets rarefied. And if this continues in this manner, we produce a train of what we refer to as longitudinal waves, made up of compression parts, rarefaction parts, compression parts, rarefaction parts. And when we measure the distance between each compression to compression or rarefaction to rarefaction, that's our definition of wavelength. And if we were to time it, put a little timer here, and we were to watch how many waves went through, how many compressions or rarefactions passed at a particular time period, then that would be known as the frequency of the wave. And if we take the wavelength times the frequency, we can determine the speed of the wave. Now, waves can travel in a liquid, a solid, and a gas, but they can't compress anything in a vacuum. So therefore, we will not have any waves in a vacuum, and therefore we will not have any sound in a vacuum. And because of the structure of the molecules in the states of liquid and solid and gas, what we're going to find out in a gas, the molecules are widely dispersed. So they're not as close together to pass on their kinetic energy to one another. So speed of sound in a gas is going to be the slowest. As the molecules get closer together and congeal and they form a liquid, the molecules are much easier able to pass on that kinetic energy, so the speed will increase. And of course, in a solid, where the molecules are really compacted, it doesn't take much space or time for the energy to pass from one molecule to the other. Now, how fast does sound travel? Sound travels at about 331.5 meters per second in air and about 1,100 feet per second. Now, that's why when you're in a thunderstorm, you see the lightning and it's there instantaneously. But it takes a while for the thunder, which was occurred by that lightning, to get to your ears, because it's traveling much slower than the speed of light. It's also true why in the old days when you saw those cowboy and Indian movies, that when they wanted to know if a train was coming down the track, they would put their ear to the railroad and see whether or not they could hear the sound of the train, because if the train was coming, the speed of the sound would be much greater, almost 5,000 times greater than the speed in air. As the temperature of the air rises, so also does the change in the speed. And therefore, it's important to know when we're measuring things that have to do with frequency and wavelength of sound, to know what the temperature is. For example, if you've ever gone to a symphony orchestra and you've listened to them tune up before the actual performance. Now, why do they do this? Because the temperature of the room may be different from where they tune their instrument last. And because the speed of the sound, which also determines the frequency of the wavelength, changes as the temperature changes, then the pitch that you hear from that instrument will change. And therefore, it's important that during each performance that those instruments are tuned to the particular temperature of the room. Now, what are some of the properties of sound? Well, there are three basic fundamental properties which are physical properties, things we can actually measure on an instrument. and they are intensity, frequency, and harmonic content. Those are physical things we can measure on an instrument, as I said. But how do we interpret those in our brain? And those interpretations, those subjective ways in which we interpret these three particular properties, are loudness, pitch, quality of the sound, timbre of the sound, how we interpret the richness of that sound. So let's talk about each one of these. What is intensity? Intensity is the measurement of the pressure in area. Now when I'm talking, my voice is going out in all directions around here. And as it's doing that, it's spreading out. And because we're talking about measuring an area, then because it's spreading out, as I go further and further away from, as the sound goes further and further away from me, then the amount of sound that's hitting a particular area is going to get less. But it doesn't go linearly. It follows what's known as the inverse square law. In other words, if I were to stand 1 meter away from where the source of the sound was, I would hear a certain amount of sound. But if I double that distance now, I'm not going to hear 1/2 the amount of sound that I heard before. I will hear 1/2 squared. And that is 1/4. So at 2 times the distance from the original sound, I'll only be interpreting that as 1/4 of the intensity of the sound that I heard at 1. And if I go back 3 times the distance from where I heard the original sound, the intensity of the sound will drop by 1/9. Now we measure intensity in watts per centimeter. Now we interpret that sound as loudness. Then intensity is it impinging on the eardrum. And as the eardrum is vibrating back and forth, the little hairs inside our ears will vibrate back and forth, convert that energy into the electrical stimulation that our brain interprets for what we hear as sound. Now, how intense of a sound can we hear? And we have a large range of sound intensities. We can go from no vibration, which we call the threshold of hearing, which we will determine to measure in the unit called the decibel. At 0 decibels, we have no motion of the eardrum. But as we increase the intensity of the sound, we can go from 0 decibels to off the limit. But at 120 decibels, we begin to experience pain. The pressure on the eardrum is so great that it actually causes us to experience painfulness. And beyond that, it's actually dangerous. We can actually puncture the eardrum if the sound is too great. Now, it doesn't go by a linear relationship. So if I go from 0 decibels to 1 decibel to 2 decibels, it's a logarithmic means, which means that to go from 1 decibel to increase the intensity to twice, I don't double it, I have to make it 10 times more. And if I want to triple the sound, I have to make it 100 times more intense. So this is what we mean by the intensity of sound and the threshold of hearing and threshold of pain. This is intensity. Now the next property of sound is frequency. How many of those vibration rates are going past a point in any particular time period? This is a physical measurement. I can measure it on an oscilloscope. I can see the number of vibrations that are occurring in a second. But how do my ears interpret that? And how does my brain interpret that? Well, that's pitch. And that's a musical kind of thing. And we can experience as a human the range of 20 cycles per second to 20,000 cycles per second. This is the audio range which we have as human hearing. As we get older, that upper range of 20,000 cycles per second will drop. Above 20,000 cycles per second, we get what we call ultra, a supersonic sound. Below 20,000 cycles per second, we get subsonic sound. Some animals work on this level of frequency. Dogs can hear much higher than we can hear. An earthquake can have a cycle in minutes where the wavelengths are huge. So we have all kinds of sonic compression waves that exist. And the range that we hear, however, is limited to the 20 to the 20,000 cycles per second. This relates to how we determine music, for example. If we would take a string, tie it at both ends, and then pluck it in the middle, the string would vibrate as one single unit, up and down and up and down and up and down. And it would a little bit to the side of the center, and pluck it again, the string will still vibrate as a whole, but now it will vibrate in parts. And if we can get this to vibrate in two parts as it's vibrating as a whole, we're now having a frequency that's 2 times higher than it was at the beginning. And this will give you a sound that's an octave higher. And if we continue to pluck it all the way through, we will get mathematical ratios for what the pitches will be from that vibrating string. And all the musical sounds that we can produce are all simple ratios of this. And if we were to pluck again the sound so it just vibrates at that one rate, just one unit, it's called the fundamental frequency. And all the additional frequencies that we put into that are called harmonics. So if we have a string vibrating in 2 parts, it's 2 times higher than the fundamental when it was vibrating at 1 part, and that's called the second harmonic. If it vibrates in 3 parts, then that's called the third harmonic, etc. And all the music that we have, depending on the structure of the instrument that makes it, will produce all the sounds that we have in the musical spectrum. For example, we take stringed instruments like the violin, that plays high notes. We take the viola, plays a little bit lower notes. If we take a cello, it places even lower notes. And if we play, for example, the bass fiddle, we get the lower spectrum of the sound. And so by taking all the instruments through the different areas and ranges of the spectrum, we can produce all the musical sounds that we can find in a beautiful orchestra. Now, what is the third property of sound? And the third property of sound is known as harmonic content. And harmonic content has to do with the shape of the wave. And the wave shape is determined by the instrument that makes the sound. And for each instrument, that sound is crafted within the instrument in a different way. And it produces, therefore, unique sounds. You will never miss an A played on a saxophone with a trumpet, say. Now, we talked about frequency before. And another characteristic of frequency is what's known as the Doppler effect. Now, you've all been standing on a corner sometime when a fire truck goes by. What do you hear? You hear the fire truck coming, gets in front of you, and goes on. And as it does, you hear a different frequency and pitch value. When it's coming, you know that the fire truck is approaching you. And when it's leaving, you know the fire truck is leaving you. And how do you know this? Now, the Doppler effect has to do with relative motion and the observer. It either can depend on you moving and the object standing still, or you standing still and the object moving, or both of you. It has to do with relative motion. If you were to just stand still and the fire truck were to stand still, the waves would be coming at you and they would be at the same frequency as they're being emitted from the source. But once we get that fire truck to move, what it's doing is it's emitting waves here when it started, and now it's moving into the waves that it started before, but it's still producing more waves. So there seems to be an area where the waves seem to be more crunched up. Now, in which case, the frequency appears to be higher. It's not. The source is still producing the same number of cycles per second that it did when it was at rest. But because of the relative motion, you experience in your ear what you experience as a higher pitch. When the fire truck gets to you, you hear the actual pitch, and when it leaves now, the opposite effect occurs. It's moving away from the waves that it made before, so the pitch drops. So, and when you talk about the Doppler effect, it's the relative motion of the waves coming in, bunching up, then decreasing on the other side. We've all heard this. We've heard it at a racetrack when the cars go around the racetrack. Next time you hear something like that, you know it's because of the Doppler effect. It's a relative motion. It's not the absolute motion. It's an interpretive thing that we interpret in the brain. Now another thing we can do is we can actually take a vibrating object. For example, let's take a tuning fork. We hit the tuning fork and we put it on a table. The tuning fork is vibrating, but we can force the molecules in the table to vibrate also at the same rate as the tuning fork. And if you do this, you'll hear the table begin to vibrate back and forth, and the hum will get larger. This is a process known as forced vibrations. But if we do this in a very particular way, we know that every single object has its own vibrational rate. All the molecules in every object that we have vibrate. And they vibrate at a particular rate which is particular to their particular nature. You've all heard this when you hear a helicopter go flying over your house and all of a sudden your dishes and things in your house begin to rattle. Well, why does that happen? Well, the helicopter rotor blades are going around and around at a certain frequency. And that frequency is now producing compression waves that's coming down. And if there's some object in your house, like a dish, for example, that's there, and it happens to have a natural frequency rate that matches that rate of the helicopter rotor blade, it will start to vibrate also. And that's when you start to hear the noises and the thuds and everything else that you hear when you hear something from a helicopter. It's also possible why you sometimes see that opera singers can sing at such a high pitch they can actually break glass. Because at that particular pitch, it will match the frequency of the glass, and the glass begins to vibrate. And if you continue to hold this pitch, the vibrations just amplify and eventually get to the point where the glass can no longer maintain that and it shatters. To do this, we talk about the property of resonance. Resonance is the matching of frequencies from one substance to another when impinged on by a compressional wave. For example, let's take a guitar, for example, and I'm going to put a little piece of paper on a guitar string and hit the guitar body with the tuning fork. Now as I do this, you'll notice that not all the strings vibrate. Only one string vibrates, and that's the string that's tuned to the tuning fork. This is known as resonance. We can also talk about the property of interference. Interference is when two waves come together and they either amplify each other or they detract from each other and destroy each other. And when we have two compressions upon each other, the wave will get intense, the amplitude will get larger. When we have two rarefactions together, it will amplify. And if we have a compression on a rarefaction, then the wave will cancel each other out. And when it does this, we produce what we call beating. You hear this in music all the time, particularly if you've studied music, you know that there are so many beats in a measure, etc. Well, what is beating? Beating is the difference between two frequencies. And these are the properties of sound.